Hello students, we are solving the IB Math A HL past papers and currently we are solving the IB Math A HL May 2022 paper 2 time zone 1 past paper. And today we will be solving the last question, that is the question number 12 of this paper. You will be getting the links to all the previously solved questions of this paper and of the other papers in form of playlist in my channel NS Online Math Tutoring Classes. So without any further delay, let us start answering question number 12. The maximum mark is 19. This contains three subparts. I have just brought in the first subpart. The question says, consider the differential equation x square times dy dx equal to y square minus 2x square for x greater than 0 and y greater than 2x. It is given that y equals 3 when x equal to 1. And the subpart E says use Euler's method with a step length of 0.1 to find an approximate value. The Euler's method will always be giving you an approximate value. It will never be giving you an accurate answer. So find an approximate value of y when x equal to 1.5. Okay, so in case you are not remembering the Euler's method, you can refer to your formula booklet. In your formula booklet, you will be seeing that there is the step size. It is referred to as h, or maybe I don't remember exactly. But step size is or step length is often referred to by the letter h. So in this case, we are having the step length or step size equal to 0.1, and the x values, it is an iterative process. So how will the x values change? The current value of x should be equal to the previous value of x plus the step length, that is 0.1. Okay. And how will the y values change? For that, I need the gradient function. Gradient function is the dy dx. So in order to get the dy dx, I have to divide the entire equation by x squared just to get rid of this x square from this side. Okay, so I am having dy dx is equal to y square over x square minus 2. Okay, so this is the gradient function. And now the current value of y should be equal to the previous value of y plus the step length, that is 0.1, times the gradient function, which is having, as you are seeing, both the variables y and x, and these will be the previous value. So it will be the previous value of x and the previous value of y. Okay, fine. So now we come to this x. So when x equal to 1, y is equal to 3. Then it will be, next value will be the previous value, the original value is 1. So the next value is 1 plus 0.1, it will be 1.1. Next 1.1 plus 0.1, it is 1.2. Then 1.3, 1.4, and finally it is 1.5. Okay, we have to get the value of y when x equal to 1.5. Now let us go to the calculator. Okay, for this we need the spreadsheet. So this is x and this is y, and these are the initial values, and for this I will be entering a formula. So I'll be entering this x equal to xp plus 0.1. And what is xp? The previous value, the original value in this case. It is 1 and it is stored in A1 cell. So it is A1 plus 0.1. Okay. Enter. And I need 1.2, 1.3, 1.4 and okay. 1.5. And this one. For this, I will be using this formula. So equal to YP, it is stored in B1 cell. So B1 plus 0.1 times, what was the gradient function? It was y square over x square minus 2. Okay. Times bracket, and we are having y square. So y square, the previous value of y, it is stored in B1. So it is B1 square over the previous value of x is stored in A1. So it is A1 square minus 2. And we just put the enter. Okay. So we have got the formula and we can get the other values of, okay, let it be like that. Okay. But we need up to 1.5, so we have got that. Let me just copy these values. For 1.1, it is 3.7. Then 1.2, it is 4.63. I am copying up to 3 significant figures. Okay. So 4.63. Then 5.92. 1.4 is 7.80. It should be 7.80. And 1.5, it is 10.7. Let me first of all write 10.6958 at least, or 10.6959. 10.6959. So therefore, y is equal to 10 point, approximately equal to 10.7 when x is equal to 1.5. Okay. Up to 3 significant figures. So this is the answer for the subpart A. Subpart B. Use the substitution y equals vx, v times x, to show that x times dv dx equal to v square minus v minus 2. And we had the gradient function expression as dy dx equal to y square over x square minus 2. Okay. From this, we have to change to this form using this substitution. So y equals vx. If I differentiate both the sides with respect to x, what do we get? with respect to x, we have dy dx equal to, now for this we will be applying the product rule. First of all, I am differentiating the x, so it is just v plus x dv dx. Okay, and in place of dy dx, I'll be substituting this whole thing in this expression. Okay, so therefore dy dx is equal to y square over x square minus 2 can be written as v plus x dv dx, and from here phi equals vx. So y over x equal to v, okay, or y square over x square is equal to v square. Okay, so dy dx, in place of dy dx, I am writing v plus x dv dx, this one, equal to y square over x square is v square minus 2. This is equal to, or let me just write it over here. This can be written as x dv dx by just subtracting v from both the sides. We are getting x dv dx is equal to v square minus v minus 2. Okay. So the subpart C, it contains 3 further subparts. The I says by solving the differential equation is this: x times dv dx equal to v square minus v minus 2, where v is y equals vx. This substitution, after this substitution, we have got the v, and v is nothing but y over x. Okay. So we have to get the expression of y in terms of x by solving this differential equation. And we are given the initial conditions as x equal to 1 and y equals 3. We have seen that, and the x is greater than 0, it is a positive number, and y is greater than 2x, so it is also a positive number. Okay, so what do? We have to solve this. So let us just separate the variables. So we are having dv over v square minus v minus 2, and this is equal to dx over x. And we have to integrate these two. So dx over x integrated, 1 over x integrated with respect to x will be giving us ln of x. That is fair and simple. But what about the left hand side? For this, let us just first of all factorize that. V square minus v minus 2. So this is equal to v square plus v minus 2v minus 2. So this is v plus 1 minus 2 v plus 1. So this is v plus 1 and v minus 2. Okay. So this is the factorized form. And so this is in fact equal to dv over v plus 1 and v minus 2 equal to dx over x. And now we are having two linear factors in the denominator of the left side. So we can use the partial fraction method. So what do? We write 1 over v plus 1 and v minus 2. This is equal to a over v plus 1 plus v over v minus 2, or we will be multiplying the entire equation by this denominator v plus 1 times v minus 2. So we are having 1 equal to a v minus 2 plus b times v plus 1, and when v equal to negative 1, 1 is equal to negative 1, negative 2 is negative 3, so it is negative 3a, and this gives us the a value as negative 1 over 3, and when v equal to 2, it is 2 plus 1 is 3, so 1 equal to 3b, and this gives us the b value as 1 over 3. Fine. So we can come to the integration part. We will be integrating, and this can be written as e in terms of this is actually this, so we can write this in place of this one. So it is negative 1 over 3 in place of a, we will be writing negative 1 over 3, or else I can just take out the 1 over 3, because both are having 1 over 3. And this one is minus and this one is plus. So let me just write this first. So I'm writing this as 1 over v minus 2 minus 1 over v plus 1 dv equal to dx over x. So this will be giving us 1/3 ln of v minus 2 minus ln of v. I am not putting the modulus sign because y over x, v is equal to y over x, y is positive, x is positive. So I am not putting the modulus sign because y is greater than 2x. So if y is equal to 2x, even then 2x over x will be 2. So 2 minus 2 will be 0, but it is not, it is greater than 2. So it should not be equal to 0. It should be more than 0. So this is a positive number. And this is v plus 1. It has to be a positive number. So therefore, I am not putting any modulus sign. This is equal to ln of x plus c, the constant of integration. And let me just multiply the entire equation by 3 just to get rid of the denominator. Okay. So this can be written as ln of v minus 2 over v plus 1 equal to 3 ln of x plus 3c, which can be written as ln of x cube plus 3c. Okay. So, and then I can bring this to this side. So I am writing this as ln of v minus 2 over v plus 1 minus ln of x cube equal to 3c, or I can combine these two as well. I am getting ln of v minus 2 over v plus 1 x cube equal to 3c. Okay, and this gives us v minus 2 over x cube times v plus 1 equal to e to the power of 3c, which is a constant number. So let me take this as k. Okay? And we have to, of course, get the value of k. For that, we are having when x equal to 1, y equal to 3. So when x equal to 1, y equal to 3, therefore x equal to 1, y equal to 3, then v will be equal to y over x, which will be equal to 3 over 1. Okay, so this is nothing but v equal to 3. 3 over 1 is 3. So 3 minus 2 over x is 1. So 1 cube and x is 3, v is 3, 3 plus 1. 1 cube is 1 and 3 plus 1 is 4. 3 minus 2 is 1. So this is 1 over 4, which is equal to k. Okay, so we have got the value of k, and so we have got the value of k, and now we have to go back to the y. We have to bring in y. Instead of v, we will be now introducing y. So in place of v, we will be writing y over x. So this is from here. I am coming to this point. Y over x minus 2 over y over minus 2, okay, x cube y over x plus 1 is equal to 1 over 4. So I can write this, I can cross multiply, and I can write this as 4 y over x minus 2 is equal to x cube y over x plus 1. Okay. And this is I can just what I can do is I can multiply the entire equation. Can I does it help me in any way? Let's see. I'm multiplying the entire equation by x just to get rid of this. So if I multiply the entire equation by x, I am getting 4y minus 8x equal to, it is getting multiplied by x. So x to the power of 4, and there is this x in the denominator. So it will be y x cube and x to the power of 4. Fine. So I'm not sure how much. Okay, now I am having some more space, I think. Yeah. So now I can I have to make y the subject. So let me just take this is x to the power of 4 is okay, x to the power of 4 is that way. Fine. So let me just take this one to the left hand side. So it is 4y minus yx cube is equal to, that means we are subtracting yx cube from both the sides and we are adding 8x to both the sides. Okay. So it is 8x plus x to the power of 4. And now we will be taking y common, and it is 4 minus x cube equal to 8x plus x to the power of 4. And so y is equal to 8x plus x to the power of 4 over 4 minus x cube. Okay. Yeah. Show that this is 8x plus 4 x cube over 4 minus x cube. Sorry, 8x plus x to the power of 4 over 4 minus x cube is equal to y, and we have shown y is equal to 8x plus x to the power of 4 over 4 minus x cube. II is find the actual value of y when x equal to 1.5, and we have found the expression of y was equal to 8x plus x to the power of 4 over 4 minus x cube. Okay, so this is II. So y is equal to, we will be substituting 1.5 in place of x. And this is a paper 2 question, so we'll be using the calculator to get the value. So 8 times 1.5 plus 1.5 to the power of 4 over 4 minus 1.5 to the power of 3. Okay. So what is the value of y? Okay, let me go to the calculator part. This is 8 times 1.5 8 times 1.5 plus 1.5 the power of 4. Okay. And this is 4 minus 1.5 to the power of 3. Fine. Enter. It is 27.3. Up to 3 significant figures, it is giving the answer as 27.3. Okay. So this is the answer for the II. It is the actual value of y when x equal to 1.5, and for the in the first subpart A, we had found the approximate value of y1 when x was equal to 1.5 using the Euler's method, and in that method we had found the y value was equal to 10.7. 10.7 or 10.7. It was 10.7. Okay. Of course, up to 3 significant figures. So you are seeing the difference between the approximate value that we had found using the Euler's method and the actual value of y. Okay. So the III says using the graph of y equals 8x plus x to the power of 4 over 4 minus x cube, suggest a reason why the approximation given by Euler's method in part A is not a good estimate. You are seeing it is definitely not a good estimate to the actual value of y at x equal to 1.5, and the all the three subparts of C taken together is having 12 marks. Okay. So first of all, we have to sketch the graph. Okay. 8x plus x to the power of 4 and 4 minus x cube. Enter. And we had given the condition that x was equal to 0, sorry, greater than 0. So we will be taking that part. This we can take as 0. And we are interested in x equal to 1.5. So let me take this as x equal to 2. Okay. Fine. This is the curve. I have taken it up to 2, and y was also greater than 0. So let me change the settings for y as well. So this is, I'm taking this as 0, the y min, and maybe I'm taking the, okay, let me take the y max as, I'm taking an arbitrary number, 50, or okay, let me first of all take 30. Okay. Okay, fine. It is just going up, concave up, and at x equal to 1.5, what is the value of y that we are getting graphically when x equal to 1.5? So graph entry, set an equation template line, vertical line, x equal to 1.5. Enter. Okay. Let me see the point of intersection if I am having any point of intersection. Because the answer is 20.7.5, I had taken the uh, y max as 30. So let me see. Yeah, we are having, you see, it is when x equal to 1.5, the y value is 27.3. Okay, fine. So, but they are saying that y is the Euler's value, the value of y that we have found using the Euler's method, so much differing from the actual value. Actually, since the graph is concave up, all through you see it is concave up. Whenever you have a graph which is concave up, the Euler's value will always be smaller than the actual value. And as you move towards, we had started with x equal to 1 and y equals 3. Okay. As you move towards greater value of x, this is just 1.5. Let us just take, let us find what is the value of y when x equal to 1. Okay. No, when x equal to 1, we can just get it from here. So it will be 8 plus 1 over 4 minus 1. So 8 plus 1 is 9 and 4 minus 1 is 3. So this is 3. When x equal to 1, y equals 3. This is perfect. But what happens when x equal to 1.1? Okay, let us see what is the exact value of y when x is equal to 1.1. So far as I remember, the y value was equal to 3.7. Okay, so let us check. I don't have to remember also. I am having the values. 1.1, it is 3.7. And you see for 1.5, it is 10.7. This is the one that I had seen. Okay. So let us see what is the value of y, the exact value of y when, what is the exact value of y when x equal to 1.1. Okay. So again, I go to this 8 times 1.1 plus 1.1 to the power of 4 over 4 minus 1.1 to the power of 3. Enter. You see it is 3.8, 3.85. And this one, the exact, this is the exact, and the Euler's value was 3.7. But the difference is quite small at this stage. Let us see what is the value of y when x equal to 1.2. Okay. Over here, 3.85 and 3.7. So it is 0.15 difference. So let us see what happens when x equal to 1.2. So 8 times 1.2 plus 1.2 to the power of 4 over 4 minus 1.2 to the power of 3. Enter. 5.14 up to 3 significant figures. 5.14. And what about this one? See, this is 4.63. Okay. This is 4.63. So it is smaller than 5.14. This was also, this one is 3.7. This is also smaller than 3.84. So whenever you are having a curve which is concave up, you should be knowing that the Euler's approximation will be giving you smaller values, values which will be smaller than the exact values. Okay. So therefore, let us write the I answer for the I. Since graph is concave up, you may draw the graph as well, just a rough sketch. And it is when x equal to 0, when x equal to 0, what happens? Y equals 0. Okay, so it will be starting from the origin and it will be, it is moving up. So this is one of the points and it is moving up. Yes, and maybe this is 1.5 and 27.3. Maybe this point is, this is 1.5 and this is 27 point. Okay. So when the actual graph is concave up, therefore the Euler's, approximate values should always be smaller than the exact values. And the difference between the two values will go on increasing as we move towards the more positive values of x. This is more of x. Okay. I have written this. If you have time, you can just show that you can just get the values of y for x equal to 1.1, 1.2, 1.3, 1.4, and 1.5 you have got. You are already having the y values for using the Euler's method. You just get the exact values and you show that the difference is just going on increasing. Okay? So this is the, uh, yeah, because it is concave up, the Euler's method will be giving you always, will be giving you some small value, smaller value than the, which will be smaller than the exact value. Euler's method always gives you an approximate answer, but that approximation will be smaller than the accurate one. So this completes our question number 12 and completes this answering of this whole paper. So in our next session, we will be starting to solve the paper 3 rather, of this time zone 1, May 2022. And thank you for staying with me till the end. I am Nilanjana Sanyal. I'm an online IB Math A, SL, and HL level tutor. I tutor students from both inside India and outside India. And currently, as you're seeing, I am solving the IB Math A, HL past paper questions. And in case you're liking my explanation, I'm solving and uploading them in my YouTube channel, as you are seeing. And in case you are liking my explanations, please to give this video a like and please to share this video with your friends so that even they can get benefited by watching this video. And in case you have any question, please feel free to write to me in the comment section. I'll be trying to answer your questions and solve your doubts, clear your doubts. And please do subscribe to my YouTube channel. It will be motivating me to make more math videos for you. So we meet again very soon in our next session. Till then, bye.